All right, welcome back everyone. In this session what we're going to talk about is, well, we're going to finish up our topic of wood, and we're also going to cover plastics. This corresponds to book chapter 6, in particular with the plastics 6.14. So let's start with this idea of timber construction. Last time what we talked about was stick-built construction, where we saw those structures with all the 2x sticking up at 16-inch on centers, and you just see a lot of skinnier lumber spaced close together. What timber construction is using big, heavy pieces of lumber spread far apart. And you can see an example of a truss here, these really big members, along with these little connectors. So it does say wood-to-wood connections. That means you're not using nails or brackets or gussets. Instead, you actually have the wood being placed inside this wood, and then you have some pegs being pushed through. I can tell that a wood member would fit in here, have a peg through here. We'll talk more about those in just a minute. So a little bit of history. This was the earliest form of construction, really. And it was heavily used up until the late 1800s, because before that time there were plenty of trees, there were plenty of people who were willing to make structures like these. And as far as the fastening systems, they weren't as common, so they were rare and expensive, right? Today it's still in use somewhat, but instead, especially with this craftsman available thing, where it used to be a very high labor-intensive activity, now we're using machines in order to carve up our joints or whatever else we may need. We also might have metal integrated connections where you have the large wood structures, but you're integrating some kind of bracket or something in order to connect them. And also laminated timbers, because we don't necessarily have the idea that trees are every which way more than we can have, right? So instead we can make our own large timbers out of smaller trees by using this laminated process. We'll talk more about that in just a little bit. So some pros and cons, since we do this with pretty much every topic. Some pros: speed of construction. So if you look at the stick construction, there were all those individual 2x that needed to be placed, and there's just a lot of parts and pieces, versus when we talk about timber construction, we have much larger pieces, but there's less of them. So the process can go much quicker, especially if they're manufactured off-site and then trucked in, right? One big advantage is you get these large spans and open floor plans. Since we have such big structural members, we can span much greater distances, opening up the floor plans. Aesthetics, most people like the way they look to have these big rigid members. Usually you're not putting a drywall or anything in front of it to hide it. Instead, you're actually letting the structure show itself. Also renewable, we can always plant more trees. Some cons: they can be prone to fire. And then dampness, just like all wood, it needs to be treated and maintained to keep this resistance to dampness away. Also finding people who can actually do this type of labor. Here's a couple examples. We have an indoor swimming pool here, and we can see these large exposed timbers now. Once again, now we do actually have metal. This is that integrated part I was talking about, where we have a metal connection between these members. This structure here looks like they're doing it more with the mortise and tenons, which we'll talk about in a little bit. But I can see these pegs and things coming through here, right? So more traditional timber framing here. There is a video on timber frame construction, and I decided for the sake of this video to skip the videos within a video. But if you want to see these videos, there's like 3 of them on these slides. Go to the PowerPoint presentation slides, also found on Canvas, and you should be able to just click on those. Just a couple more examples. I can see I have these large spans in here using this timber construction. And here I see some of the connection fitting together in some way. So speaking of that, looking at the joints, we can have a wood-to-wood joint if we were to create a hole, and this is called a mortise, and then had something that would slip in there, that's called a tenon, and then these pegs would go through here and lock the whole thing in place. So this is like the 2 pieces, or actually 4 pieces if you can include the pegs, and this is the after it's put together, right? Same idea here, but now we could also have the tenon go all the way through the mortise. And in this case, we're using these keys. See how these are like wedge-shaped to lock it into place. So as I pound these in from this backside, it'll suck everything together, right? Once again, there's a video you could go to Canvas and take a look at of someone actually making these framing joints. And in that video, what you will see is they make them with a mechanical, more like a press. We can also make our own large timbers. This is a process of taking a series of smaller pieces of wood and then laminating, gluing them together, right? So we have individual pieces of dimensional lumber. So we talked about like 2x4s would be a dimensional lumber, right? Bonded together with structural adhesive. So we have a layer of glue, and we have a layer of glue, and a layer of glue. This is an advantage because we can use these smaller trees. If you look at some of the traditional timber design, there are these massive trees that we are shaping into the structural members. Well, we don't always have access to that many large trees. So if we can harvest a tree when it's much smaller, we can pull out like a 2x4 dimensional lumber and then stack those together. And that's what this means here, harvested from the second and third growth forests and plantations. Some benefits we have compared to just normal dimensional lumber, we have a much greater strength and stiffness, and we can have some very large spans like we see in this picture here. So continuing on with this idea of glue lambs, like I said, this would be like basically 1.5 inches thick, which is like a 2x4, and the width is about a 2x4, up to about about 11 inches, right? Once again, here's a video you could watch the process of actually making glue lambs. And in that video, it actually has that Bob Vila from This Old House, so it's worth watching. So using it in residential construction, I can see that this is a glue lamb, is a primary beam, and then I have these I-joists coming in. Because we already know I-joists, we learned from our last video, that the I-joists are much stronger so I can have a greater span. Well, the problem with that is you have a whole lot of load if you have a big span coming right here, so we have to support that greater load. That's why we're using this glue lamb, because it's even stronger since we have all these individual layers glued on top of one another. It's a massively stronger beam. Here we can see an interior application, once again using the metal for the connection, but we have these glue lambs coming all the way across through here. And here we see a glue lamb header for it looks like to be a garage. Same idea. This is kind of cool. So this is a glue lamb arch, right? The way they do that is when you have a smaller, like a 1.5 inch thick member, you can actually bend it. So you bend it, and then if you take another member, put glue on it, and then bend it to the shape of the first member, and continue that process as you build out, the whole structure will remain in this arch shape. So that's the process of what they use to do something like this with these glue lambs. Here's a massively deep one here, right? And you can make these as deep as you want, right? So I think in the one video with Bob Vila, it actually talks about making some like 10 feet deep or something. So, and here's more of a commercial application. You can see the aesthetics. Looks kind of cool to have them exposed. Notice with all these, we're leaving them exposed just because we like the way it looks. But of course, that means they do have to be treated in a way to keep them from deteriorating in the environment. So that's going to wrap up our conversation on woods. Let's move over to plastics and how we use plastics in the construction industry. There's really two major categories of plastics we're going to talk about. One is thermoplastics, the other is thermosets. And with thermoplastics, the way those work is they can be heated and softened or cooled and hardened multiple times, and they will still retain their main characteristics, right? They're dimensionally stable at room temperature, meaning they aren't going to grow too big or too small. Some examples would be ABS, acrylic, nylon, cellulosics, polycarbonate, polystyrene, and vinyls. On the other side, we have these thermosets, and what a thermoset is once it's cured, once it's set up, it starts off usually in a liquid state, and once it sets up, it can't be softened again. So it has better heat resistance, greater stiffness than the thermoplastics, more difficult to form and more brittle, more limited construction applications. We'll look at those in just a little bit, but now we're talking about epoxies or fiberglass reinforced plastics, polyester, or silicones. So we can also modify our plastics by adding some ingredients during their fabrication process. We can add plasticizers. And we use that same word when you're talking about concrete with a superplasticizer, which basically makes it more fluid, right? Well, same idea with plastics. What we're doing is we're making it more flexible, more pliable, more impact resistant. Basically, it's the same thing as like if I were to heat up a plastic, you can imagine how it's more pliable and flexible and it won't want to snap. Well, same idea with these plasticizers. And you can see you're using these with the thermoplastics, not so much with the thermosets. We can also add fillers. So a filler, as the name implies, actually is just an extra material that is making it more volume of the plastic. And we could do that because we want to increase the bulk or reduce price. It can change some things like the hardness, toughness, heat resistance, electrical resistance. So you have to keep that in mind. We can also add a stabilizer. And one of the big issues with these plastics is that plastic will break down with UV light. So if it's out exposed outside in the sun or wherever else there might be UV light, the plastic will eventually start to degrade and break down because it's absorbing these UV rays. So what we can do is add this stabilizer, and that stabilizer will absorb those rays and not let it actually go right into the plastic. So we can look at the structural properties of plastic, the strength of plastic, in tension, which we talked about, compression, and bending. Tension is the most important with plastic. It's actually very strong in tension. It's comparable to wood anyways. It's not as much as steel, but comparable to wood. We can look at the stiffness. So stiffness is more important to plastics than strength. It does have less stiff than steel or glass. And thermosets, if we compare thermosets to thermoplastics, thermosets are stiffer than thermoplastics. We can look at creep. And what creep is it's a change in material under a prolonged stress, as it says. So if I were to hang a weight from, say, a 12-inch piece of plastic and just let it sit there for, I don't know, weeks, months, right? Eventually I see it just starts to stretch very, very slowly. That's called creep. And this does occur more often in plastic than other materials just due to the chemical composition of the plastics. We can talk about the toughness of plastic. So the toughness has to do with how much it can move and bend and everything before it actually breaks. So that's why it says strength combined with resilience, because if the strength is when it starts bending, and then how much can it go before it actually breaks. It can measure the impact strength, generally measured as impact strength. Plastics are much better in impact resistance than wood, concrete, glass. So this is one of its key characteristics, is it can be very tough. Hardness, abrasion resistance, this is not the strength of plastic. They do not perform as well as a glass or a steel. So if we have a glazing, then it will scratch a little more easily than something like a glass. Some other properties, we have expansion and contraction when it is heated or cooled. It's much higher in plastics than other building materials. And because of that, what we would need is the room for them to expand. So if we're using it as a construction material, then we need those expansion joints. Conductivity. Plastics are excellent heat insulators, especially foam plastic. We'll talk about this more in just a second with one of our uses for these plastics. But basically, it doesn't allow heat to conduct through it very easily. Much lower thermal conductivity than metals. Their corrosion resistance. So basically, they will break down in UV light, but not in a high humid environment. They don't corrode like a steel would do, right? And also, chemicals are not as big of a deal unless they're some specific ones that attack plastic chemical structures. So plastics should be chosen carefully based on what kind of exposure you're going to have to these corrosive conditions. Fire resistance. So plastics do burn, and some are even extremely flammable and can release these toxic fumes. So that's something we have to take into consideration. We can add some additives. I know we didn't talk about this earlier, but another additive we can add would help combat this burning issue. And IBC will actually have a rating scale for these plastics based on the rate that they burn, how easily it will burn, and how fast that burn will spread, right? All right, so let's talk about where we actually see this stuff in the construction industry. So there's a lot of words here, right? Thermoplastics. Let's start with, I think it's acrylonitrile butadiene styrene. Basically, you know this is ABS, right? So ABS is what you see for all of the black plumbing that you see in houses and in construction projects. You'll see it for drain water, wastewater, and also for venting throughout the structure. We have acrylics. So acrylics, skylights, roof domes, light fixture panels, light diffusers, corrugated sheets for roofing panels. Here's an example of a skylight right here made out of acrylic. We can have cellulosics. Cellulosics are like, you can use them for handrails, tool handles, adhesives, and coatings. So if you've seen the exterior handrails that are made out of plastic, there's a good odds it might be made out of cellulosics. Continuing on with the thermoplastics, we have fluorocarbons, or in particular we have polytetrafluoroethylene, or what you might know it as is Teflon. So the main characteristic of Teflon is it's a very low friction, right? So you would use it if you had, for some piping, if you needed materials to slide through the piping, so some corrosive chemicals. Movement pads where you need a low friction to move heavy furniture or something. We have nylons like a wire mesh, carpet fibers, rollers for door, windows, gears, cams. Kind of see nylon all over the place. I pulled a picture of a nylon wrap around a scaffolding system where the nylon is used as a barrier to keep either things from falling off, or sometimes if the wire mesh is tight enough, it'll be like a deflection for wind. And sometimes you can even heat inside there. We have, continuing with the thermoplastics, polycarbonates like safety glazing, light fixtures, lighted signs, molded hardware. Here's a safety glazing on this, looks like a greenhouse type structure. We have polyethylene, could be used in like temporary fencing, vapor retarders, countertop protection. We have polypropylene. You might see this in siding, moisture barrier. I threw a picture up here of concrete fiber reinforcement made out of polypropylene. When we were talking about concrete, we talked about GRFCs, glass fiber reinforced concrete. This is another fiber, concrete fiber. It's just more of a plastic fiber as opposed to the glass fiber. We have polystyrene. So polystyrene, or an expanded polystyrene, is called styrofoam. That's actually a name of a brand, right? And this is largely used for insulation. So you'd see it on pipes, floors, walls. This guy look like he's putting styrofoam or polystyrene all throughout his house to insulate it. We also have vinyls. One of the most common that you'll see in construction is polyvinyl chloride, PVC. A lot of people mix up PVC and ABS because both of them you'll see in residential construction. The difference is one is white and one is black. So the white is PVC, the black is ABS. And there'll be different glues to combine them and everything else, right? Other places you might see this: sheet and floor, tile flooring, gutters and downspouts, moldings, sidings, window frames, piping, drainage systems. So I see a guy putting together some plumbing here. So moving on to the other side of things with our thermosets. So with our thermosets, now we're saying, it's more like a one-time application and it's just done. We're not reusing them. So we have like epoxies, and that's like a adhesive or a coating compound. Either you're going to epoxy over something to give it a protective barrier, or you're going to create an adhesive out of it. Here we see that these rebar, it looks like, are epoxied into this slab. So say you had a slab and you wanted to have an expansion on the slab and you didn't have any embeds or anything, you could drill into the side of the slab, squirt some epoxy in there, which is like a semi-liquidy type of state, put in your rebar, and then it sets solid, creating a connection that's very strong, and you could build off of that. We have melamine. So melamine is like it's like this laminate. It's this white, very slick laminate on top of this. Looks like an MDF. And you see this a lot of times in like cabinets or laminate countertops, things like that. We have these phenolics. I think I'm pronouncing that right, but I have no idea. I had to look this one up to be honest with you, and actually one of the main things was for formwork, and I come from the formwork industry. But basically, it's if you have it on the face of the formwork, what it does is it makes it a smoother surface, so it'll release from the concrete easier. We talked when we were talking about concrete about coating the formwork with like a release agent. Well, if it's a smoother surface, it releases a little easier. Electrical parts like sockets, switch boxes, circuit breakers, things like that. Continuing on with thermosets, we have polyesters. This is a glass fiber reinforced polyester, right? And you can do things with that like roof sections, shower stalls, sinks, cabinets, bathtubs. Polyurethanes. Now we're talking about, so this guy's spraying polyurethane for an insulating, a spray foam, right? Because these have great insulating properties. Or it could be the core material in a SIP, which is the two panels with the insulation in between. Silicones. We have sealants and coatings on masonry walls. This is like looks like a bathroom application because it is very waterproof. If you get 100% silicone, you'd use that in a waterproof caulking situation. So that's what I have. That wraps up our whole topic of wood and plastics. Next up will be steels, so look forward to that. And once again, let me know if you have any questions or comments. Talk to you all later. Thanks.